All right, welcome. Today, we're going to pull back the curtain on something we all use every single second we're online, but almost never actually see. We're talking about the invisible shield that protects our digital lives. We're talking about encryption. You've seen this little guy a million times, right? That little padlock up in your browser's address bar? We all know it means things are secure. But what does that actually mean? How is that tiny icon standing between your private info and, well, the rest of the world? It's a great question. The best way to think about it is like this. Encryption is your personal digital bodyguard. It's on duty 24/7, making sure your conversations, your credit card numbers, your secrets stay secret. So let's go ahead and follow this bodyguard on the job and see exactly how it works, step by step. Okay, so first things first, we need to understand why we even need a bodyguard in the first place. And that brings us to this fundamental problem of the internet. See, the internet, by its very nature, is a public space. It's an open network. So sending data without encryption is kind of like standing in a massive, crowded room and just shouting your credit card number for everyone to hear. Anyone who wants to can just listen in. Yeah, not exactly secure, is it? This is where our bodyguard's work begins. So before you can even think about sharing any secrets, you have to solve an even more basic problem: trust. How does your browser really know that when you type in paypal.com, you're actually talking to the real PayPal and not some scammer pretending to be them? Well, the answer lies in something that's basically a digital passport. And this passport is officially called a digital certificate. It's an electronic document that proves a website's identity. But here's the important part: who issues these passports? It can't just be anyone. They have to come from a highly trusted third party, kind of like a gatekeeper for online identity. So let's take a peek inside this digital passport. What's so amazing is that your browser checks all of this in milliseconds. First, it looks at the common name to make sure it matches the website you're trying to visit. Then it checks the issuer. That's that trusted authority we just talked about. And finally, it checks the validity dates to make sure the passport hasn't expired. It's this lightning-fast identity check happening completely behind the scenes. And that issuer? It has a name: a certificate authority, or a CA for short. You can really think of these CAs as the official, highly secure passport office of the internet. They're neutral third parties that do all the hard work of making sure a company is legit before they hand over one of these digital passports. They're pretty much the foundation of trust for this whole system. Okay, so our browser checked the website's passport. It confirmed its identity. Awesome. Now for the really clever part. How do your browser and the website agree on a secret code to talk to each other without anyone else eavesdropping on them making the agreement? This is where something called the secret key exchange comes in. Now, to get how this works, we need to know about two basic types of encryption. On one hand, you've got symmetric encryption. This is super fast because it uses just one single shared secret key for both locking and unlocking a message. Simple. On the other hand, you have asymmetric encryption. Now, this one is genius. It uses two keys: a public key that anyone can have, which is only for locking things, and a private key that only the owner has, which is used for unlocking. And here's the magic: something locked with a public key can only be unlocked by its matching private key. So here is the secret handshake that brings it all together. It's so cool. First, your browser just grabs the website's public key. It's sitting right there in that digital certificate. Second, your browser creates a brand new temporary symmetric key and immediately locks it up using that public key. Third, it sends this locked little package over to the server. Now, since it was locked with a public key, the only thing in the universe that can unlock it is the server's private key. So the server unlocks it, and boom! Both your browser and the server now have the same secret symmetric key. So just to be clear, the slow, super secure method is used for just one thing: to safely deliver the fast key that's going to protect the rest of the conversation. Pretty clever, right? The handshake is done. We've got a secure, private channel. So now what happens to your actual data as it travels back and forth? Now, this is a really important idea to get. Your data is protected by encryption in two different states. When it's in transit, flying across the internet, it's protected by that secure channel we just set up. Think of it like putting your data inside an armored car. But what about when it's at rest, just sitting on your phone or on a server somewhere? Well, that's where things like full disk encryption come into play, which is kind of like a secure vault for your stored info. You absolutely need both for total security. Okay, so we've covered confidentiality, keeping secrets secret, and we've covered authentication, making sure we're talking to the right website. But there's one last critical piece of the puzzle: integrity. How do we know the message we just got hasn't been secretly changed along the way? The answer is a totally fascinating mathematical trick called hashing. A hashing algorithm can take any piece of data, a sentence, a whole movie, anything, and it runs it through this special one-way function to create a unique string of characters. This string is its digital fingerprint. You can never go backwards to get the original data, but you can use it to prove that the data hasn't been changed one bit. Let's see it in action. It's pretty neat. So here's that classic sentence. When we run it through a common hashing algorithm, we get this unique fingerprint right here. It will always produce this exact same hash for this exact same sentence. But watch what happens if we change just one single character. We switched dog to dot. Now look at the hash. It's completely different. This is what they call the avalanche effect. Even the tiniest change creates a totally new fingerprint, which makes it incredibly easy to see if data's been tampered with. And this hashing technology is actually the secret sauce behind digital signatures. A sender can create a hash of their message and then encrypt that hash with their private key. When you get it, you use their public key to decrypt the hash. If it matches the hash of the message you got, you know two things for sure. It came from them and nothing has been changed. It's the ultimate tamper-proof seal. So let's put it all together one last time. The digital certificate is the passport that proves who you're talking to. The secret handshake securely agrees on a secret code. The armored car of TLS protects the data while it's moving. And the digital fingerprint from hashing guarantees it hasn't been messed with. All of these layers work together in the blink of an eye to form that invisible shield, your digital bodyguard protecting you every day. And all of this brings us to one final really important question. These basic principles we talked about, proving identity, verifying integrity, they're more crucial today than ever before. In a world of AI and deepfakes that are getting better every day, how will these same cryptographic tools have to evolve to help us prove what's actually real? It's a huge challenge, and it's one that's going to define the future of digital trust. Thanks so much for joining me.